to be represented by an infinite dimensional Hilbert space. So we really don't look too much at x, y, and z directions for position. Occasionally there are circumstances where it helps, but normally you just think about this position basis. And each of the coefficients in the position basis represents essentially the square root, as you'll see, of the probability that the particle is here, or here, or here, or here. So there's a coefficient for the particle being here, there's a coefficient for the particle being here, there's a coefficient for the particle being here, and each of those represents a dimension in the space. In addition to position and momentum, other bases that kind of have some physical intuitive sense to them would be things like angular momentum and energy. And energy is going to end up being especially important. So the most important operator, remember an operator takes state vectors and transforms them. The most important operator in quantum mechanics is called the Hamiltonian operator, which is another fancy name, it's named after Hamilton, is another fancy name for the energy operator. And so it's just the kinetic energy plus the potential energy. And when we put that into this Ket notation, what you've got is the Hamiltonian operator operating on an energy eigenstate transforms the eigenstate back into itself, but with some change in magnitude. And this eigenvalue is the amount of the change in magnitude. So the energy that you measure is the eigenvalue of this transformation. So the energy operator operating on an energy eigenvector gives you the same eigenvector back, stretched or squeezed by an amount that's the energy. For a non-relativistic particle, like a slow-moving electron, for example, you'll normally see it written as 1 over 2m times the momentum operator twice. Sometimes you'll see this as p squared. So this is momentum squared plus whatever potential there is. And potential is often a function of position. Right? Then this is potential energy. So this is kinetic energy and this is potential energy. And if you think about the classical way of writing potential energy, you can find that momentum squared over twice the mass is also the kinetic energy in classical mechanics as well. So the Hamiltonian is really important, and I'll come back to why in a second. So just to make it clear again, if we have some operator Q operating on an eigenvector of that operator, then the system is in an eigenstate of the operator. It gives us back that same eigenstate with an eigenvalue stretched or squeezed by the eigenvalue. So the other thing that we can do is, just like we can have vectors that are combinations of unit vectors, like a vector that goes in x, y, and z, we can also have what are called superpositions, which are the sums or a linear combination of several basis vectors in whatever basis we're choosing to look at. So if we have a discrete case, which is we have maybe 5 different possible measurement values, so we have 5 eigenvectors and 5 eigenvalues, then each of the eigenvalues for whatever combination, whatever superposition we want, is multiplied by a coefficient, and we just sum them together. And if we do that, we find that when we take, remember we said that the eigenvectors themselves will have, the state vectors will have a magnitude of 1. And if we take a superposition and find its magnitude, then we find that the sum of all the different coefficients squared, and this is their magnitude, so that this number can be complex. So all these coefficients can be complex. You multiply each coefficient by its complex conjugate, that gives you a real number, and then you sum them together, and because the eigenvectors themselves are normalized, that means they all sum to 1, you get that the coefficient squared for any superposition state is also 1. And this is going to be really important because we're dealing with these complex numbers and we need to get a way to tie ourselves back to reality. And this is what's going to do it for us. And if we have a continuous case, then if you're comfortable with calculus, then you'll recognize that the sum just turns into an integral. And if calculus is not your thing, if your thumb's down on calculus, then don't worry about it. This is just another way of saying a sum. Now, I'm using x here, which is often used to denote position for a continuous variable, just to give you an example, because this is a good way of introducing what's often called the wave function. So the wave function is all the coefficients of this superposition vector in the position basis, or in whatever, usually in the position basis. The momentum basis, for example, will be continuous as well. And energy, interestingly enough, energy, depending on the system, can have discrete, maybe 5 or 7 or 25 specific values, or it can be continuous. Or there's even situations where it's discrete in some energy ranges and continuous in other energy ranges. So the main thing I want you to take away from this is that just like we have x, y, z is one way to represent x, y, z is another way, x diagonal, y diagonal, z diagonal is another way. These vectors that we're looking at have some reality independent of the basis in which we're studying them. And so there are many different ways to make these superpositions of basis vectors in whatever basis we choose to come up with a vector that has some significance to us. So now we get to the famous Schrodinger equation, and what the Schrodinger equation tells us is how the system changes with time. So the state vector, so any state vector, if I know what that state vector is now, and I want to figure out what it's going to be 5 seconds from now, I can use this equation. So there's two constants. I is our favorite imaginary unit. H bar is Planck's constant divided by 2 pi. Planck came up with this constant that he called H, which he kind of put in for reasons of matching things with experiment. And it's often more useful to write H over 2 pi, but some of the physicists got tired of writing all those over 2 pi's, so they just shorthanded it and they scratched a bar through the H. So that H bar is just Planck's constant divided by 2 pi. So it's just a real number. And then the d by dt here means the change in time of the state is given by the Hamiltonian operator that we just saw, this energy operator operating on the state vector. So now if you know the state at one time, you can project forward what it's going to look like at later times in the future by solving this differential equation. Now, if we have a vector, remember we can choose whatever basis we want to write it in, and then it's going to show up as a superposition of the eigenvectors in that basis multiplied by some coefficients. So if we do that, then what we can find, so this is still Schrodinger's equation. Here's the coefficient for each energy eigenvalue and the energy eigenvalue. All right, same on 2 sides because we have the state showing up on 2 sides. And we work through the math here. And what we find is that the coefficients basically evolve with time according to a complex exponential. My favorite complex exponentials. So what we find is if we can write any state vector that we're interested in as a superposition of energy eigenvectors, then the time evolution of the coefficients for each of those energy eigenvectors will evolve in a very, very simple way. So it's the initial one multiplied by this complex exponential. And sometimes in a quantum physics course, you'll see this referred to as a rotation of the phase. The amplitude and the phase is this complex exponential term. So if that doesn't mean anything to you, that's fine.
Can I ask a question?
Yeah.
Sorry, I'm kind of lost. For the Schrodinger's equation, can you find it? So you talked about the Hamiltonian before, and it was an operator for the energy state.
Correct.
But now it's also IH bar d by dt.
So
So
basically what Schrodinger found was he tried to come up with an equation that would allow you to predict if you knew what if you knew what the wave vector was, or if you knew what the state vector was at a given time. he wanted to find an equation that would describe how you would find it at a later time. Okay? So far so good?
Mm-hmm.
And what he found was that the time derivative of the state vector happens to be equal to the Hamiltonian operating on the state vector.
Well, does that mean that the Hamiltonian is the equivalent of the first part of the left-hand side?
Yes. Well, it's actually, so you often substitute the Hamiltonian for one for the other in your equations. And so the Hamiltonian, in addition to being the energy operator, happens to also correspond to the time evolution operator.
Is that a definition or a coincidence or some awesome physics result?
That is some awesome physics result that happens to I mean, you can write any number of different, in fact, Paul Dirac tried to make this more compatible with special relativity and came up with a slightly different version of another differential equation. But this happens to work really well in experiments.
Is that something specific to psi, or does it work for any state vector?
It works for any state vectors. This psi can be any state vector.
That's weird.
Yeah. Oh yeah, I changed notation here a little bit, because before I was calling psi the wave function, but a lot of, I wanted to put this in because a lot of sources, a lot of physicists use psi just for a random state vector. So I changed notation a little bit on you here.
And here the state vector is a combination of the positions, momentums, and energies that you defined before.
So the state vector is, this is super key to quantum mechanics. The state vector is whatever happens to be the state of the system at the time. So you can write the state vector as a bunch of positions, or you can position vectors, or you can write the state vector as a bunch of momentum vectors, or a bunch of energy vectors, or a bunch of angular momentum vectors, or you can come up with some crazy complicated set of vectors that you want to use as your basis. But remember, vectors have some reality independent of the basis that you choose to describe them with. So the state vector doesn't care whether you're in the momentum basis or the energy basis or wherever.
It's not on the basis.
I was going to say, so I h bar d by dt of the state vector of the system is the energy of the system?
It turns out, yes.
It's not obvious.
It's not obvious, but it turns out that you can do experiments that show that that actually works really well.
So the energy operator is same as energy, or?
So, yes and no. If you do an experiment where you measure the energy of a system that is in an energy eigenstate, the energy that you measure will be the eigenvalue of that eigenvector. Okay, yeah, now you're starting to see that that's weird, right? Good, that's the first, that's weird. There will be more. There will be more here in just a minute.
So are there any restrictions on the state vector, how it should be?
The state vector needs to have a magnitude of 1.
Okay.
That's it.
If you use the state vector with position as your basis,
Mm-hmm.
then I understand how you can represent potential energy, but how do you define kinetic energy?
That'll depend on the system that you're measuring. So that depends on how does P look in the position basis? How does momentum look in the position basis? And we'll talk about that probably in the third part of the talk. Okay? Great questions, everybody. Okay, how's that time? Okay. So the last piece here, I think, the last piece here is measurement. So I just outlined what happens if you're in an energy eigenstate, right? So there we go. Let me rehash that for any eigenstate. Come on. So if the system is already in an eigenstate of the observable being measured, then the measurement result will be the eigenvalue, and the system remains in that eigenstate. Which is to say, if I know that my position is here, and I measure the position, I will get here, and it will stay here. As long as the position is, and it will stay here as long as the position is also an energy eigenvalue. Because remember, then the phase will rotate, and we can talk about that later if you want to get that. But anyway, if I know that the state is in a certain energy, then I know I'll get that energy every time I measure, basically. Okay? So if the system's in an eigenstate already, then you get the eigenvalue corresponding to that eigenvector, and it stays in that eigenstate and then it evolves with the Schrodinger equation. On the other hand, if you're in a superposition of eigenstates of the observable that you're measuring, remember the observable is the transformation. Transformations have eigenvectors, and the eigenvectors correspond to eigenstates. And so if something is not already in a single eigenstate, it can be in a superposition of eigenstates. So each eigenstate has its coefficient for the state vector. State vector is the sum of the coefficients times the eigenvector. That's our basis. And it can be whatever it is, Q can be position, momentum, angular momentum, whatever you want. Now, how do you know which result you're going to get? We knew we were going to get the eigenvalue when we only had one eigenvector to work with. But now we have possible measurement results are these Q. Quantum mechanics says we can't get more than one result. We can't get something that's a mixture of these eigenvalues. We have to get an eigenvalue. So you will get one of the eigenvalues, and the probability that you will get that eigenvalue is the magnitude squared of the coefficient, which remember may be complex. Coefficient may be complex. The magnitude squared will be real and positive, which is good because we want probabilities not to be negative. We also want probabilities not to be greater than 1, which is why we demand that eigenstates have a magnitude of 1. The basis fact that state vectors have a magnitude of 1, so that we can get actual probabilities. And here's another thing that you may find surprising. As soon as we measure and we get one of those eigenvalues, then the system is reset into that eigenvalue. And that's called wave function collapse. So let me tell you why this is and then after the measurement, the same as before, the new state changes with time from that eigenvector or eigenstate into whatever it gets to by way of the Schrodinger equation.
Who decides which eigenvalue to return?
It is, according to the assumptions of quantum mechanics, it is irrevocably and irreducibly random. It is a source of true randomness. Yeah, everybody that has a computer science background will know about pseudo-random numbers. People actually use quantum systems to generate true random numbers.
But over a period of time, the percentage will be according to the probability.
Correct. If you make the same type of measurement on the same type of system over and over and over and over again, okay, so if I have 1,000 electrons and I put all of the electrons one at a time into this state and then measure something else, and then this same state, measure something else, the same state, measure something, measure that other thing, then I'll get a probability distribution for the possible eigenvalues that I can get out of it, and those eigenvalues will show up in proportions proportional to the magnitude squared of the coefficient there.
Once you measure that first electron, can you never measure it again because you collapsed it?
So if you measure it again,
Or you can't get the data you want?
So let's say you collapse it into an energy eigenstate to make things simple. So you take the electron, it's in some superposition of energy eigenstates, then you measure it. It now, if you measure it again, will be in that energy eigenstate. Here, let me give you a kind of a concrete example. Let's see how we're at.
So you can only get one result after the first time.
So you stick, it's trickier if what you're measuring is not compatible with energy, which is to say that it puts the system into a superposition of energy eigenstates, because then those energy eigenstates will evolve. So for example, if you have an electron and you measure it to be here, and the position and energy eigenstates are not compatible with one another, which means to say that the position eigenstate is a superposition of energy eigenstates, then what you'll find is that if you measure it immediately after, it will be here. But with time, the wave function will spread, because Schrodinger's equation will spread the wave function. So then later you might measure it over here, or back where you measured it, but it'll be a probabilistic measurement. Let me give you an example here. Can we get the device set up? Yeah. I can probably reach it better over here, yeah. Lisa was nice enough to let me borrow her polariscope for this. So, has anybody played with polarizers before?
right here.
Yeah, exactly. Exactly. So, here's a there's a light source under here, unpolarized light comes out. There's a polarizer here, and there's a polarizer up here. Okay? So,
There's a big fat light gonna come out the front because
Oh,
of
is it?
anything.
Okay.
It's gonna be just. It also goes up.
so when I turn this on, the light comes on and some of the light comes through here. Great. Okay? So now, I'll try to do this way so that everybody can see. If I turn the polarizer up here, it gets lighter and darker. So it's the same brightness out of here, but I turn this lighter and darker. So what we're doing with this, and also with this polarizer, is we are measuring the polarization of photons that come through these two. So polarization has two eigenvectors, and we usually call those eigenvectors horizontal and vertical. Sometimes it's useful to call them other things, but we usually call them horizontal and vertical, just like we had the two eigenvectors in my squishy animation. This filters out only photons with one polarization, so let's call that horizontal. So we know that all the photons coming out of here are in the horizontal polarization. If they're not, they get absorbed by the polarizer, and they don't get through. So all the photons that get through are in the horizontal polarization. So if the top polarizer is also in the horizontal polarization, then all the photons get through it too. And if the top polarizer is in the vertical polarization, we know they're horizontal coming out of here, so this will absorb all of the vertical, or all of the horizontal polarized photons, and there's no vertical to get through. So far, so good? Okay, now what if we do this at an angle? So how do we know how many of these photons get through? Well, now these photons are in a superposition state for the eigenvectors of this polarizer. So this polarizer's horizontal and vertical are now superpositions of this polarizer's horizontal and vertical. So therefore, at random, photons are selected to either be parallel to this one or perpendicular. And the closer they are, the closer these polarizers are to align with each other, the more likely it is, the higher probability that the photons will line up polarization with this second polarizer. So that's why it gets brighter and darker. Okay, so far so good? Now, this is where things get a little bit screwy. Okay, so now I've got the polarizers perpendicular to one another. So horizontal coming out here is vertical here, they don't get through. Okay? Now I put a third one in here. So this will absorb anything that doesn't match it. Put a third one in here, and it lights up again. Now how is that possible? Because I'm absorbing here, and I'm absorbing here, and I've absorbed all of them. But now some of them are getting through when I add another absorber. That's wave function collapse. So the photons that get through the second polarizer are collapsed to be in the eigenstate parallel to this polarizer. And therefore that's going to be not perpendicular to this polarizer, and so therefore some fraction of them will also get through. So that's the end of the main quantum mechanics section. So we have about 15 minutes left, maybe just a little bit less if you guys want to take a quick break, play with this. The next thing I'm going to run through is a detailed example of how you can use quantum mechanics. Actually, one of the earliest problems was for what's called black body radiation. And it's basically a thermal object emits light, and I'm going to show you how you can figure out how much light it emits at different wavelengths. And then I'm going to go through a number of more advanced topics in quantum mechanics. I'm not going to dive into any of them. I'm just going to give you an overview and give you some ideas of what you can research if you're interested in this a little bit more. Any questions, or anybody want to break?
Is that the quantum computer, the qubits, is the same thing where they observe it and the state collapses?
Correct, correct.
And with some probability it can be any of.
Yeah, so that's one of the topics that I'll briefly touch on in the next section, but yeah. So quantum computing, so that the quantum algorithms utilize the fact that superpositions kind of test all possibilities at once.
Yeah, I could
And,
never understand that.
So yeah, I have a good book that I'll recommend for you on that
Oh,
too.
perfect.
Yeah.
Thanks.
So how do you determine, like if I have some electron, how do you determine what state vector do you want?
Depends on the system and what you're trying to find out about it. So if you know, oh sorry, something accidentally I logged out a little bit. It depends. So a lot of what an undergraduate quantum mechanics course like these would be, especially this one, is figuring out, okay, if I know the potential energy layout of whatever system I'm in, whether it's a box or whether it's an atom with a nucleus pulling on an electron or whatever it is, then what are my energy eigenstates going to look like? And if I can, and so solving for energy eigenstates is a lot of what you do in a quantum mechanics course. And then once you know that, you'll know, sometimes the energy eigenstates themselves are super complicated. So if you imagine like an electron on a spring, energy eigenstates there are pretty complicated, but if you have some combination of position and momentum, then they actually get very simple. And so you can often pick the simplest eigenstate for the math, or the simplest eigenbasis for the math, based on what you're seeing from the energy eigenstates. Or sometimes you just want to know, there's some quantity that you want to measure. I want to measure the polarization. So it really makes sense to have the polarization states be my eigenvectors.
What are the properties of the particle or whatever we are talking about to satisfy all these criteria? Like electrons, photons, or is it across the entire scale of?
So ideally with quantum mechanics, you should be able to model anything. So whether you're talking about strings, or quarks, or nuclei, or atoms, or molecules, and there's a lot of quantum mechanical modeling of even complex molecules. It's computationally intensive, but you can do it. When you get to like baseballs, quantum mechanics actually reduces to Newtonian mechanics, nicely enough. And it's easy to show that in some cases, it's harder to show that in others. But then you're probably better off using Newtonian mechanics. But in principle, you could keep using quantum mechanics if you had a powerful enough computer or you were good enough at math. If you get up to galaxies and clusters of galaxies, in principle, quantum mechanics should work, but there's no good way to put gravity in quantum mechanics. And so much of their behavior is determined by gravity that, in principle, quantum mechanics should work, but it's hard to see how. Okay, so applications of quantum mechanics. So we're going to talk about black body radiation. I don't like that term because it doesn't really mean much to the everyday person. It certainly didn't to me for a while. So just think about your oven. If you have an electric oven, and you turn on the heating element in the oven, and it's dark at first, and then when it gets hotter, it gets red, and it gets hotter still, it gets whiter. It changes color based on how hot it is. And people knew this. That things changed colors, and they wanted a way to explain how much of what color was coming out of an object at what temperature. So to go back to quantum mechanics for a second, and then we'll come back to the experimental results later. What we find, and there's some derivations for this, with momentum being what's called a generator of translation, but in most quantum mechanics courses you just kind of take this as a given. Momentum operator is actually minus IH bar times the position, the derivative with respect to position. So the change in the wave function with position tells you it's momentum. Completely counterintuitive, but it works. And what that really means is that if you have a superposition of positions, so remember these are the coefficients, the wave function, These are the position basis vectors. Remember, we get infinite number of those because we have a new basis, we have a new dimension for each position. If you operate on that, integral is just a sum over all the possible positions. Then you get minus I h bar. I is our favorite complex number. H bar is Planck's constant divided by 2 pi. And then you just take the derivative of this set of coefficients with respect to position. You do it twice, like in the Hamiltonian, then sometimes, and as I said, this is often written p squared. Then you get minus h bar squared, the i's give you a minus sign, a third minus sign, and then you get the second derivative of the position with respect to, or the second derivative of the wave function with respect to position. And when you have d squared by dx squared, you start thinking waves. Because the wave equation in classical mechanics has a d squared by dx squared on one side and a d squared by dp squared on the other side. And so a lot of times Schrodinger's equation is called Schrodinger's wave equation, because the p squared in there leads to a second derivative with respect to position. And when you hear about particle wave duality, what that really is that you can write something as a superposition of position eigenstates as a particle, but you can also have some wave time evolution, wave-like time evolution to its state. So when we use that, another useful, really useful basis is what I'm calling the plane wave basis. Many of you will know it as a Fourier transform. Complex exponential, here we are again. So we have the complex exponential, there's position here and time here, and the number that's multiplying the position is called the wave number, k, and the number that's multiplying the time is angular frequency. These are both real numbers, but they can be negative. Usually omega is positive, k can be negative. And k tells you kind of about the direction and how fast the peaks and valleys of the wave are moving in space. And the omega tells you kind of how fast it's oscillating up and down in a single point. If you think about waves on the ocean. If you're bobbing up and down in one place, that's omega. If you're letting the wave push you, then that's k. So we can cheat a little bit and derive some very common, and usually these are just givens in any quantum mechanics class, but I like to think of them as signifying some Fourier transform. So the momentum is you take the position derivative of the wave function, so the change in wave function with space gives you h bar k times this psi, the plane wave. So that's an eigenstate. And so therefore the eigenvalue should be h bar k. So the momentum is h bar k, if we're going to measure it. And let's use Schrodinger's equation. You were asking, can you swap, whenever you have an h, can you swap in an I h bar d by dt? Well, if you do, then you get h bar omega popping down from your derivative. And so therefore the energy eigenstate, the energy eigenvalue should be h bar times whatever the frequency is, the angular frequency. No, it's not really legitimate, but it's what we call a hand-waving argument. Because it's simple, and you can talk about it in a 90-minute talk. So,
But those results are for if your wave function is a plane wave.
actually, they're really kind of used for everything.
No. I don't think that's
But yes, essentially what you're implicitly moving into this plane wave basis.
Okay.
Now, because we're running out of time, I'm just going to skip ahead real quick here, so I'm going to skip over a bunch of the math. But what we want to figure out is for this... Oh, we have the room till 5:30? Oh, okay, great. So does anybody need to go at 5, or can you need to go at 5? Okay. Okay, so let me get through this piece by 5, and then I'll talk about some of the other applications and some references for the next 5 or 10 minutes after that. And so first we're going to ask, for this thermal body, how many states, so we have energy is proportional to the frequency in this plane wave basis. So how many states are available at some particular frequency? And we find if we have two polarizations, remember polarizations, we're working with photons here for our thermal source, so what we find is that the, what's called the density of states, the number of states available within a particular width, d omega of some frequency, is equal to this expression. So it goes with the square of the frequency. And the idea behind that is, if you think about all the different wave vectors that the wave could have, it could be going this way, it could be going this way, and you measure out a certain space with the same magnitude of wave vector, then what's the surface area of a sphere? What's the equation for the surface area of a sphere?
4 pi r squared.
4 pi r squared, right? So you basically have the surface area of this sphere in wave vector space. So you've got 4 pi k squared. And then your angular frequency has to be reduced to regular frequency, so you got to get rid of some 2 pi's, and that's how you figure this out. And then you convert, because for photons in a vacuum, the wave vector and the frequency are actually very closely related by the speed of light. So that's how you get this equation for the number of states for a particular frequency. And then for each available state, how many photons should we be able to expect in that state at a given temperature? And that's a question for thermodynamics. And basically the probability should go with some exponential decay inversely proportional to temperature, which is to say, if it's very cold, we don't expect there to be a lot of high energy states being occupied, which means we don't expect there to be a lot of photons just naturally floating about, which means the T is low, so the decay goes fast. So N, the number of photons in that state, is not very high. Remember, the energy of each photon is h bar omega. And we only have individual photons, so the number of photons is quantized. It's discrete. It can be 1, 2, 3, but it can't be 1 1/4. And so that's where this quantum word comes from, because in many systems have solutions that have discrete solutions rather than continuous solutions. So we can make sure that it's a probability by normalizing it correctly, and so the actual probability is given by this formula.